Hello and welcome back. In the previous lecture, we looked at finite differences and a lot of important concepts. Now, let's start off by looking at finite volumes, and this will be a solid stepping stone for moving towards finite elements. So, what are finite volumes? So, they are a method in which we discretize the domain into cells, which we called as control volumes. We apply conservation laws on these control volumes. So this depends on the physics, how these conservation laws are written, that depends on the physics. Then from these conservation laws, we derive a bunch of flux balance equations, and we apply these equations over these control volumes, and then we solve them to get the solution. Okay, so let's do this step by step, and it's instructive to look at the diffusion problem, which we looked at in the finite difference case, the very simple diffusion problem. So this is a very simple case in which the domain is just running from 0 to 1, and this is a boundary value problem, a steady state problem, right? So the boundary values are u is equal to 1 at x is equal to 0 and u is equal to 0 at x is equal to 1. So in finite volumes, we discretize the domain into cells. So let's just do that. Let's consider 3 cells here, each of length 1 by 3. So in finite volumes, the next step is that you save the cell values and average cell value at the cell center. So there are many different methods in finite volumes. There are a lot of different schemes. So I am going to look at only the simplest one. Okay. So in the simplest case, we just consider the cell average value and store it at the cell center, and just say that this cell average just holds all over the cell. Now this is fundamentally different from our finite differences. In finite differences, the argument was discrete and only applied on each node. Okay, so we did not say anything, rather we don't know what happens inside rather between these two nodes. Okay, only we stored nodal values. Now here we are saying that the cell average value holds at each and every x coordinate inside the cell. Okay, so now instead of using summations, here I can start writing an integral. Okay, so this kind of an approximation can be called as a piecewise constant. Okay, because inside every cell you have inside every piece, okay, every piece or every cell, you just have a constant representation. So if I want to find out the value of u inside this cell, I can just integrate, which means I can find out the area under this box, and I can do the same for every cell, and you will have different boxes. Okay, here and they will all be constant. Okay, so this is piecewise constant representation. Now since we can integrate, we can write an integral conservation statement based on the physics that we are studying, and this can be converted into fluxes by using the divergence theorem. So we'll have a look at that. So the good point about this is this ensures perfect flux balance. So what goes in comes out. Okay, and this is the key behind why it is so famous, and from a CFD and transport perspective. Okay, so let's try to understand this step by step. Let's try to first have a look at how to do this conservation statement. Okay, so a typical conservation equation, you could think of it as a mass balance equation or a heat balance equation. So in this case, let's look at just mass balance. So let's just consider a concentration here. Okay, the concentration can be thought of as density into mass fraction. Okay, and this is your fixed law of diffusion, which can be written as Q is equal to minus K del C. The minus sign basically represents the fact that the flux occurs from it has a direction, and it occurs from where the concentration is high to the point where the concentration is low. Okay, so this is your fixed law of diffusion. Okay, and this is your diffusion equation. Okay, so now we'll have to derive this diffusion equation in this problem. So let's consider this control volume. You could also, for analogy, you could think of it as a pipe. You are writing a mass balance over a pipe. Okay, so how would you write the mass balance on this control volume? So you would write this simple statement that rate of change is equal to in minus out, or inflow minus outflow, plus what is getting accumulated. Okay, or what is getting formed. So let's start writing this step by step. So the units for each of these terms are going to be kg per second. Okay, so here we just write our concentration integrated over the control volume. So concentration as a unit kg per meter cube multiplied by the volume. So this is kg per the unit of time, kg per second. Okay, so this is your rate of change, right? dc by dt, your rate of change. in concentration. This is your accumulation term now. This is a source term which can be thought of as a reaction, Kc, a first order reaction, second order, and so on. So this also has units of kg per second, and so this term shows how many kgs are being formed per second. Okay, so this is a simple diffusive case, right? We are solving this problem, so these two terms will be zero. We have a steady state case here. So we are just looking at inflow minus outflow. Okay, so now inflow minus outflow can be written as the divergence of the flux, and if you just expand this out, you will just get your diffusion equation back. Okay, so you will just get del square C minus K del square C, which is your diffusion equation. But let's try to understand this, why inflow minus outflow gives rise to this kind of an equation. So for this, let's understand the del term, the gradient term, and the divergence term. So let's try to understand the concept of the gradient first. Let's consider this cone. I'm showing the top view and almost a side view, so this will give us some better idea. So let's consider that we are climbing on this cone, okay, and we'll encounter these lines with constant heights. Okay, so these are called as iso lines, okay, or iso contours, where the height is constant. Okay, and to understand the gradient, we have to understand so we have to basically apply the del operator on a scalar. Okay, so the idea behind the gradient is applying the del operator on a scalar. So we need a scalar here, and the scalar is the height. Okay, so I have already defined this in the introduction, but let's try to understand it better. So let's say we start walking across this surface and we stop at point P. Okay, and now we are interested in finding the gradient. Okay, so this is the del operator. It is a vector operator as well as a differential operator. So let's apply this on the gradient. Okay, think of I and j as unit vectors in the x and y direction. So what is this term? Okay, this is basically the x component of your gradient. Okay, so what is dh by dx? So this is the slope along this direction in the x direction, right? And this is dotted with or you could think of not dotted, I'm sorry. So this is this has a direction, and this directional component is this I, okay, the unit vector in the x direction. Similarly, if you look at in the y direction, there is a height. The height is increasing. Okay, and this is the slope. Okay, this is the magnitude. So this is the magnitude of the vector is dh by dy, and you can see this gradient, right? So I have also given a gradient inside this arrow. So the height is increasing. Okay, here the height is decreasing. Okay, and it is having a direction which is the y direction. So if you look at this side view, this y direction is acting perpendicular to the screen. Okay, almost perpendicular to the screen. Okay, so this is your y direction and this is your x direction. So this is your gradient. Now what would happen if instead of a scalar we have a vector? Okay, so this is like a vector field. Okay, so what would happen if this was a vector instead? So we could apply a cross product to the vector or a dot product. Okay, so divergence is basically the dot product of the vector. Okay, so let's consider this vector u. So let's consider this geometry, which is discretized into 9 squares. Okay, so we'll look at only the middle square. Let's consider a vector u here. Let's think of u as any vector. It could be a velocity. So these are your velocity components in the x and y directions. We have broken this vector into two parts. I and j are unit vectors in the x and y directions. Okay, so now how would I understand del dot u? So that would simply be dotted, the del operator dotted with this term. Okay, so this would since this is a dot product, this is scalar, this would give me du by dx plus dv by dy. Okay, and u is the x direction velocity, v is the y direction velocity. So what does this really mean? So this means that any change occurring in u in the x direction will be balanced by an equal and opposite direction change in the or equal and opposite magnitude change, I'm sorry, in v in the y direction. Okay, so let's say there is a packet of fluid which is being pushed out by this velocity u, okay, in this direction. Okay, so there is a gradient in this direction. Okay, there is a slope in this direction. So this slope, the magnitude of this line will be perfectly balanced by what comes in from the y direction. Okay, so this means that whenever the fluid packet is pushed from here, from these two cells, fluid packets will come in and replace this. Okay, so that is basically your divergence equal to 0 kind of concept. Okay, what will happen inside these cells now? So if there is a y direction flow from these cells, there will be an x direction flow from these cells. Okay, because the same equation holds. Naturally, if there is an x flow in these cells, there will be a y flow in these cells. Okay, so now you can look at this as vortices. Okay, so nice vortex is forming here. Okay, so this is what happens in your incompressible flows, right? And you can see this here. This is a velocity flow in a lead driven cavity. Okay, that is what I have shown here. So hopefully I have understood what is the divergence equal to 0 condition. So what would be divergence is equal to a constant? So if I have a big slope here, a large gradient here, so that is just being balanced by small gradients. Okay, which means that there is a net outflow. Okay, so this brings me to the key concept. Divergence is a measure of inflow minus outflow. Okay, so this is what we wanted to understand. So now we could just replace U by Q, which is you could think of as the diffusive flux. So the divergence of the diffusive flux is the diffusive inflow minus outflow. Similarly, you could think of the convective flux, which is concentration into velocity. So divergence of convective flux would be convective inflow minus outflow. So now let's just plug this in into our equation. So we are also setting the convective term 0 here, because we don't this is a purely diffusive problem, but this will help us understand the convection diffusion equation and the scalar transport equation when we move to finite elements. So presently we are just getting divergence of Q, the flux, is equal to 0. So this will break down into your diffusion equation. So now we have derived our diffusion equation. Now what we do in finite volumes is we use the divergence theorem. So very simple way to understand this. Look at this statement. Any gain or loss of mass inside the cell must be accounted for by the mass flowing across its faces. So any change by diffusion that is occurring here will obviously, from where will it occur? It will just occur from the faces, right? It will just move out from the faces, right? So here this is your divergence of flux or applied on the control volume. So and this is the integral which is applied on these boundaries. Okay, d omega. These are your boundaries. So this is your flux dotted with the unit normal in the outward direction. Okay, and you could also write this as a summation across these boundaries. Okay, so now we are in a position to formulate the flux balance equations. So let's write this down for our 1D case. So this orange part is the integration inside the control volume, and Q dot unit normal in the outward direction. So here I have shown this unit normals. Okay, and this is my flux minus K du by dx at these two edges. Okay, so this is my flux balance equation, and in finite volumes mainly I am interested in this flux balance. Okay, so now let's go ahead and apply this for our problem, right? So let's just consider the second cell first. Okay, this is running from x3 to x5. The length of this cell is 1 by 3. So all of these cells are equidistant as well. I mean perfectly equal. Okay, so the distance between these cell centers is also 1 by 3. Okay, this is the unit normal in the outward direction. Here it is +1 and here it is -1. Okay, simple x coordinate direction. Okay, it's simple 1D problem. So now my equation which I want to solve is this. Okay, the flux balance equation. So this has to be applied at H3 and H5. Okay, so let's approximate this at edge 5 first. Okay, so we will use the central difference approximation, and we, for this recall the equation which we have already learnt, where we use 3 points to approximate du by dx. Okay, the first derivative. So this equation is basically the slope at x5 can be computed from x6, the values at x6 and x4 as follows. So u6 minus u4 upon the distance between x6 and x4, that which is 1 by 3. Dot it with the unit normal. Do the same thing at edge 3, just the unit normal is -1. So this is my first equation, and I can reduce it to this equation. Okay. Now let's look at cell 1. X3, the treatment for X3 node is pretty similar, so I will not expand that. Same as before, central difference approximation. What happens at X1 is slightly different because the boundary is getting terminated at X1. So I can just do a forward difference where the difference between X2 and X1 is 1 by 6. So U2 minus the value at the boundary, which is 1. So U2 minus 1 upon 1 by 6, okay, and then dot it with the unit normal in the outward direction. But this is order of h accurate. So to maintain consistency, we do a manipulation. We consider a ghost point outside, and we just say that this ghost point x1 is basically equidistant from the ghost point and x2. Okay, so we make an approximation. We say that u1 is basically the average of the values at u0 and u2, and from this we calculate an imaginary ghost value. U0 is equal to 2 minus u2. This is simply just a manipulation, because if you write a central difference approximation here between x2 and x0, so this is u2 minus u0, this value, upon 1 by 3. So this will just reduce to 2u2 minus 2 upon 1 by 3. So this is same as u2 minus 1 upon 1 by 6. So this is just a manipulation. So this will reduce to this equation. Now let's go to the next slide. We'll take the third cell. Okay, we'll consider a ghost point here as well. We'll do exactly the same thing and get the third equation. So now we have three equations, three unknowns. Solving them will give me these values at the cell averages, and these are lying perfectly along the analytical solution. U is equal to 1 by x. Okay, so this is the solution. So note what's happening here. So the area under this analytical solution is a trapezius, and I am modeling it with a piecewise continuous, which is a box. Okay, but what's happening is the box is overshooting here and undershooting here. Okay, and the areas are perfectly matching. Okay, so that's your piecewise constant approximation, and this can introduce some errors, and using some other methods you could even flux you could just model this. Instead of piecewise constants, you could even model the curvature. So there are so many different advanced finite volume methods. So but this is the most simplest method, and here the error is primarily coming from the fluxes. Okay, and we are using central difference approximation, so the error is order of h square there, and so the main error is basically that error. Okay, but there is also an additional contribution of error coming from this approximation. Okay, so that is our finite volumes, and we learnt a lot of key concepts here. We looked at divergence, we looked at the convective flux, the diffusive flux, we looked at piecewise constants. Okay, so all of this will be really key in understanding finite elements quickly. So that we'll do in the next lecture, and I thank you for paying attention, and I will see you again.